Let's jump right into this explainer. If you spend any time deploying apps or managing environments, you know Linux is essentially the beating heart of the DevOps world. But, you know all that raw power? It's a double-edged sword without the right guardrails. So today, we're going to demystify the core mechanics that keep Linux servers locked down and prevent catastrophic downtime.
I want you to picture the sheer chaos for a second. What if 100 developers, QE engineers, and managers all shared a single unrestricted root login on a production server? Literally, just imagine the disaster if someone accidentally deletes a critical system folder, like the /sbin directory, simply because everybody's using the exact same administrative account.
You'd get immediate system corruption, complete disaster, and the worst part? You'd have absolutely zero way to trace who actually made the fatal error. When everyone is root, you have total system chaos and zero accountability. Well, that high-stakes nightmare is exactly what Linux file permissions are built to solve. They exist to contain the blast radius and ensure order. Here is our roadmap for this explainer. We'll start with why file permissions matter. Then we'll cover users, groups, and others, followed by read, write, and execute. After that, we'll break down chmod with numbers and symbols, and chown for managing file ownership. Finally, we'll wrap up with some real-world DevOps examples.
Section 1. Why file permissions matter. Let's see how Linux establishes order out of all that potential chaos.
So, file permissions are essentially Linux's out-of-the-box automated guardrails. Even if you have proper user management set up, you still have a massive problem if every unique user can just read and modify everyone else's files, right? So permissions step in to complement your user management. They draw the hard boundaries so one user absolutely cannot accidentally nuke another user's critical files.
Moving on to Section 2, users, groups, and others.
What's actually pretty brilliant here is how Linux categorizes every single person trying to access a file into 3 distinct buckets. First up, the user. That's the specific owner who created the file. Then you have the group, which is a collection of users the owner belongs to, like the dev or QE team. And lastly, others, which is literally everyone else on the server outside of that group. By structuring it this way, an admin can change access for, say, 250 developers all at once just by tweaking the group permissions. Way easier than updating 250 individual accounts.
Section 3, read, write, and execute. Let's talk about what these 3 groups can actually do once they get access.
Every single file on a Linux machine evaluates 3 exact actions. Read, which is pretty obvious, you can view the contents of the file. Write, which is the really powerful one, you can modify, update, or even delete the file. And execute, which is absolutely vital for us in DevOps because it lets you actually run the file as a script or program.
Now, when you run a lists command in your terminal, you're going to see this 9-character string, something like rwx, rw-r-. That is a visual map of exactly what the user, group, and others are allowed to do. The first 3 characters belong to the user, the middle 3 are the group, and the last 3 belong to others. And if you spot a dash instead of a letter, that just means that specific action is explicitly denied for that group. All right, Section 4, chmod, numbers, and symbols. Let's look at how we actually change these default permissions. This brings us to the famous 4-2-1 math rule, which I love because it perfectly translates human intent into machine security. Instead of constantly typing out user equals read, write, execute, Linux assigns a simple number to each action. Read is 4, write is 2, execute is 1. To set your permissions, you literally just do the math. Let's look at a real example with the chmod command. If you run chmod 750 on a script, you instantly grant full access to the user, read and execute access to the group, and you completely lock out everyone else. Why? Well, 7 for the user is 4 plus 2 plus 1. The 5 for the group is 4 for read, 0 for write, and 1 for execute. And that 0 for others means absolutely no access whatsoever. It is so incredibly efficient. On the flip side, we have the infamous chmod 777. Running this gives read, write, and execute permissions to literally everyone on the server. You are basically telling the system that any random person who logs into that server has full rights to change or delete your file. Obviously, this is incredibly dangerous and should almost always be avoided. Section 5, chown, managing file ownership. What if you need to actually transfer the ownership of a file to someone else entirely? Before we change owners, keep this analogy in mind.
The folder is the bank, and the file is a locker inside that bank. You cannot access a locker if you aren't even allowed inside the bank itself. Folder permissions will always take priority over file permissions. So if a QE engineer is blocked at the directory level, giving them full rights to the file inside does absolutely nothing.
To actually change who owns the file, you'll generally need administrative privileges, so switch to the root user. Let's say a developer leaves the company. An admin can use the chown command to safely hand over their critical scripts to a new QE user. The syntax is super straightforward. Chown, the new user, a colon, the new group, and finally, the target file.
Section 6. Real-world DevOps examples. Let's anchor all of this into a highly common scenario you've probably faced.
If you've ever tried logging into an AWS EC2 instance and immediately got hit with that dreaded "permissions are too open" error, yeah, it's because your private SSH.pem key is vulnerable. AWS actually blocks your connection on purpose because your sensitive credential file has permissions that might let someone else on your system read it. To fix it, AWS strictly requires you to run chmod 400 on your PEM key. This ensures only you have read access, while completely locking out the group and others from seeing your credentials. Remember the math? That 4 gives the user read access. The first 0 means the group gets nothing, and the second 0 means others get nothing.
So as we wrap up this explainer, I want to leave you with this question to reflect on regarding your own environments. Are your server's access keys truly locked down to 400, or are you unknowingly running 777 in production right now? You know, today might just be the perfect day to open up your terminal